Hey everyone, in this section we're going to be going over chapter 2.5, which is linear functions and models. So our linear function is the function of the form f of x equals ax plus b, where our slope is equal to our a and our y-intercept is equal to our b. So we want to find out if a function is linear, and then if so, we're going to give the f of x equals ax plus b form. So for our first one, we have f of x equals 2 plus 3x. So yeah, this function is linear because it's already in our required form, and our a equals 3 and then b equals 2. So for our second one, we have g of x equals 3 times 1 minus 2x. When we distribute the 3, we get negative 6x plus 3. So yes, it's in our linear form. And our a equals negative 6 and our b equals 3. So for c, we have h of x equals x times 4 plus 3x. So this is 4x plus 3x squared. So this is not a linear function because we have an x squared, and we want it to not have the squared, but the squared makes it quadratic, so it's not a linear function. And then we have k of x equals 1 minus 5 of x over 4. And so I do the heart thing here to see where the 4 needs to go. So I have 1 over 4 minus 5 over 4x. And so yes, this is a linear function with our a is equal to negative 5 over 4 and b equals 1/4. Alright, so now we're going to show that slope and our average rate of change are the same thing for linear functions. So let fx equals ax plus b be a linear function. If x1 and x2 are different values for x, y1 equals f of x1 and y2 equals f of x2, then x1, y1, and x2 and y2 are on f. So our slope that's equal to y2 minus y1 over x2 minus x1. And our y1 and y2 are equal to f of x1 and f of x2. So we'll go ahead and change those. So we get f of x2 minus f of x1 equals x2 minus x1. And this is equal to our equation for our average rate of change. Therefore, the slope and average rate of change are equal. So slope and rate of change for a linear function, fx equals ax plus b. The slope of graph f and rate of change of f are both equal to a, the coefficient of x. Therefore, a equals slope of graph f equals the rate of change of f. So for linear functions, we just call it rate of change. We don't call it average rate of change because it stays consistent. So for example, we have a dam is built on a river to create a reservoir. The water level f of t in the reservoir at time t is given by f of t equals 4.5 t plus 28. So our t is the number of years since the dam was constructed, and then f of t is in feet. So for our first one, we're going to sketch it. So I just went ahead and plotted the y-intercept 28, and then I did 4.5 as my slope, and then I plotted the next point and then drew the line through it. So I went up 4.5, and then I went up 4.5, and then one there, up 4.5, and then one across. So my rise over run. So our b is what's the slope. So we know the slope is from our linear function, 4.5. So our slope is 4.5. C is at what rate is the water level in the reservoir changing? So we know that our rate is going to be our coefficient of t, which is the slope. So our rate of change of f is 4.5. So that's going to be 4.5 feet per year. So don't forget the units when we're doing rate of change for applied problems. So in making and using linear models, we have the slope of the graph of the function is the rate of change of one quantity with respect to another. So if our a is 6 gallons over 3 minutes, that means our rate is going to be 2 gallons per minute. And here we can see a graph of this as well. So the gallons are these, and then our minutes are these. So here we have an example. Water pumped in a pool at 5 gallons per minute. Initially, the pool has 200 gallons of water. So for a, we want to find a linear function v modeling the volume of water in pool at time t. So our VT equals AT plus B because it's a linear function. We know our A is equal to 5 because our slope or rate is 5 gallons a minute. Our B is 200 gallons. So that's the amount of water we had to begin with. And we know that because at T equals 0, our V0 equals A0 plus B is equal to 200. So our B is equal to 200. So our VT is 5T plus 200. So for part B, pool has a capacity of 600 gallons. How long will it take to fill the pool? So we basically want to find the T where our volume at time T is equal to 600. So we have 600 equals 5T plus 200. And so we find that T equals 80 minutes to fill the pool to a 600 gallon capacity. Okay, for our next example, we have John and Mary are driving west at constant speeds. The graphs show the distance y in miles they've traveled from Philly at time x in hours. And we have our x going from 0 to noon. So at what speeds are John and Mary traveling? Who is traveling faster? How is this represented by the graph? So by the graph, we can see the different distances they traveled and at what times. So we're going to go ahead and find John's speed by using the graph and then our average rate of change formula. So we have John at 2 p.m. had traveled 250 miles and at 4 p.m. had traveled 350 miles. So using our average rate of change formula, we have 350 minus 250 over 4 hours minus 2 hours, which is 50 miles an hour. We have Mary's speed, and so at 2 p.m. she had traveled 150 miles, and at 4 p.m. she traveled 300 miles. So we use the average rate of change equation again, so we have 300 minus 150 miles over 4 hours minus 2 hours, which is 75 miles an hour. So we can see that Mary is traveling faster than John by using these average rate of change equations, since 75 is greater than 50. We could also see this from the graph because Mary's graph, her linear model, is steeper, so she has a steeper line and greater slope than John. Okay, now we want to find functions that model the distances that John and Mary have traveled as functions of x. So our f of x equals the distance John traveled at time t. And we know it's linear, so our f of x is going to equal ax plus b. So we found our a in part A, which is 50 miles an hour for John's speed. And then his y-intercept is b, is 150 because that's the distance here we see that he started at. So that's his y-intercept. So f of x equals 50x plus 150 for John. So Mary's is a equals 75. The 75 is the part that we calculated from part A. That's her slope or rate of change. B equals 0 because she didn't start at any distance, so that's her distance started, or y-intercept is 0. So our gx equals 75x. Okay, how far will John and Mary have traveled at 5 p.m.? So we're going to go ahead and see what the distance is that they've traveled. So our t is going to be 5. So we'll go ahead and use the functions that we modeled in part B. So for John, f of 5 equals 50 times 5 plus 150, which is 400 miles. For Mary, that's 75 times 5 equals 375 miles that she's traveled at 5 p.m. Okay, now we want to find when Mary overtakes John and at what time that happens. So Mary overtakes John at the time when they traveled the same distance, at time x, when f of x equals g of x, as distance is y. So we have 50x plus 150 equals 75x. So we want to find the point of intersection in the graph. And so if we solve for x, we do 75x minus 50x equals 150. And then if we divide 150 by 25, we get x equals 6. So Mary overtakes John after 6 hours, or at 6 p.m. Okay, I'm going to go ahead and continue the next video with chapter 2.6. See you there.